Hi guys, Dr. Mattis here, trying to talk to you today about oxidation reduction reactions. This is one specific type of a chemical reaction. Our last video we talked about all sorts of types of chemical reactions. A mess of them in a really long video, way too long. But here we go, oxidation reduction reactions. This is basically just a transfer of electrons. No bond break-in, no bond make, well, sometimes. But for the most part, we're looking at electrons being moved from one atom to another, so charges are changing. And some double replacement reactions, you have an iron 2 on one side staying an iron 2, just who he's hooked up with changes. Not so in oxidation reduction. An iron 2 might become iron 0, might be a 3 positive instead. That's what we're talking about. We're going to have a couple quick definitions. Oxidation is when they lose electrons. Reduction is when they gain. And so we have this groovy little thing, Leo goes Kerr. Loss of electrons is oxidation, gain of electrons is reduction. You'll see some more about this as we go. Alrighty, let's look at a reaction of copper 2 with iron. Copper 2 is making copper, iron making iron 3. If we look a little bit closer into that, you'll see that, hey, copper goes from plus 2 to 0, and so iron is 0 plus 3. So when copper goes from plus 2 to 0, for that to happen, copper has to combine with 2 electrons to make a neutral copper. For iron to become iron 3, 3 electrons have to be separated from the iron. Okay? By our definitions, copper gaining is going to be a reduction. Iron losing is going to be an oxidation. Those are just straight out definitions. Okay? Alrighty. The thing that you might ask is this question I put up here to remind myself to ask it, where's the third electron? Iron lost 3, copper gained 2. Cool. If I lose $3 and you pick up 2 of them, where's the third dollar? Floating around in the ether, somewhere. It's got to be there. So we need to balance it, okay? And there's this thing down here you're welcome to look at while I chit-chat at you real fast. Basically, it's going to be copper and iron reactant, and we got to figure out the ratios, just like when we balance. Well, 2 electrons and 3 electrons, 2 times 3 is 6. Well, let's have this thing happen 3 times. Okay, so we get 3, 6, 3. And let's let that other reaction happen twice. So we get 2 irons on each side, 6 electrons. Okay, because then this 6 electrons here and that 6 electrons there, they're going to cancel out. Alrighty, so the electrons cancel because they're on opposite sides of the arrow, and we end up with a groovy little happy little balanced equation. Okay, and that should make sense to you, but the problem that a lot of students have is figuring out where these electrons go. Okay, and so to figure out where they go, which is a loss, which is a gain, I just have a quick analogy for you of a guy gaining a $100 bill. Okay, to gain a $100 bill, the $100 bill wouldn't show up as a product. You would have some dude separated from money, having it now tucked in his pocket. All right. Well, she can have 100 in her pocket. When she loses it, she's separated from it. Okay, so a loss is a separation. A gain is bringing them together. You're not going to see the electrons once it's gained because it's tucked inside the electron cloud, much like that $100 bill tucked inside your pocket. Okay, let's do a quickie example. Iron, copper, tin. Okay, so you got tin 4, copper 1, making copper 2 and tin 2. Let's inspect that by the oxidation numbers. Okay, well, we got 4 and 2, 1 and 2. That means we got plus 4 to plus 2 for tin, plus 1 to plus 2 for copper. Okay, if tin is going from plus 4 to plus 2, you need 2 negatives on this side to make them equal. We're adding negatives because electrons are negative. For a plus 1 to a plus 2, well, which side can you add negatives to? This side has to have a negative added to it. And that's why we end up with these half reactions there. Okay? Tin is definitely gaining, so that's a reduction. The electrons are now combined with the tin as one thing. It's been gained, like that $100 bill. Copper's lost it. Okay? And so copper is now separated from her money, from her electron. Alrighty? If you use this methodology, you could just look at things and balance them, but I have to get to something kind of a bit complicated, because what if you have this reaction, this unbalanced equation here? To balance this puppy, like a lot of students would say, well, I got 4 oxygen, so I need to put 4 there. That makes 4 manganese. So I had to put a 4 there, which makes 16 oxygens, which makes 6. I mean, it's just back and forth. We need to end up with something that looks like this. We need some different methodology, man. You know what I'm saying? Okay. Well, I have everything written there. You can take a snapshot of that, screenshot it, pause the video, that sort of gig. There's two methodologies here. It basically hashes out with adding three things in here. We need to add the electrons in to balance out the loss and gain of electrons like we saw in those other half reactions. We also need to balance oxygens like I just showed you with that permanganate gig with this 16 blunder to 4 blunder, okay? We need to add oxygens. And since we're taking place in water, we're going to use water. And we're going to add water in. And if it's acidic, which most of these are, we're going to add acid in the form of H positives, okay? So whichever methodology you find favor with, awesome. I'm going to show you kind of two ways. I got two examples coming up, okay? First is just to balance this groovy little half reaction here of the iron and the permanganate, okay? Say we have that under acidic conditions, okay? We can balance the iron pretty easily. Iron to iron 3, so we need to add an electron. As far as the manganese goes, I added a bunch of stuff in there, okay? But a lot of students can do this two different ways. One is, this is 4 oxygens, so you need to add 4 waters to balance the O's. 4 times 2 is 8 H's, so you add 8 H positives. You then have on this side 8 positives and a negative for a total of 7 positives. And over on this side, you have 2 positives. So we have to add 5 negatives in the form of the electrons to balance it. Personally, I hate that methodology. Okay. Another way you could look at it, and that's why I gave that previous slide to you guys, is manganese here is a +7. Here is a +2. Difference of 5, so add in the 5 electrons. Okay. Balance your waters. Already, we got 4 oxygens here. Okay, that means we're going to have 4 waters there. That introduces a bunch of hydrogen. Don't freak out about that. You got 8 hydrogens. Slide back here, slap in 8 H positives. Whichever way you go, it'll work. Okay, personally, I would also add that eventually you're going to do this in your final equation. I'll show you that later. Okay, whichever way you go, whichever way fits your psyche, do it that way. You'll end up with the right answer either way. Okay, but once you get there, we're going to have to then cross multiply to cancel out our electrons like we did earlier. Okay, and then we just add that whole thing up again, and we're good. Okay, but if you have acidic conditions, you could add basic conditions, and basic conditions come up when teachers are mean to you and they just want to throw it at you. Okay, balance it as if it's a half reaction under acidic conditions, and then neutralize that acid, the H positives, by adding hydroxide. So let's go back to that other one that we just did. We ended up with that equation there, and if you notice, we got 8 H positives. We're going to have to neutralize that by adding hydroxide base. And so we add hydroxide, but we add to one side, we add to the other. It's still balanced. Just a trick, but it's still balanced. Okay? But now you got to realize, okay, I got that. Well, these guys are going to combine to make water, and that'll make 8 water. Okay? So we have 8 water on this side, 4 waters on that side. We'll cancel out 4 of the waters. Okay? That's going to become 4. That'll become none. And we'll have our final equation. Okay? It's just a trick. Don't freak out when it says hydroxide. Don't try to balance it straight off. Oxidation with hydroxide. It's a mess. It can be done, but it's easier just to do the acidic and then do a couple extra steps. In this case, adding a couple steps is easier than starting over. Alrighty? One last example. Hey, let's do this reaction, see what we get. First, we got arsenic, okay, and nitrogen. Arsenic, it looks like up in here, I have them as a +3 to a +5. Well, if each oxygen is a -2, okay, 3 times 2 is -6, and we have 2 each arsenic, so it has to be a +3 to balance that out. Over here, same gig, we got +3 from the H's. 4 oxygens make a -8, so the arsenic has to be a +5. Similarly for the nitrogen, +5 to +2. If you really want more on oxidation numbers, I have another video on my website where I slow down. I just we can hash out the oxidation numbers. But there we got arsenic +3 to +5. That's a difference of 3 electrons. Nitrogen +5 to +2, difference of 3 electrons. That should make it easy. Okay, so if you look at those half reactions, all I did, okay, was add in the electrons. Okay, and that's all right. You got +3 to +5, which is 2 electrons. I think I said 3 earlier because I messed up my math. That's 2 electrons, but we have 2 arsenics. Okay, so that's going to be a total of 4. Okay, it's not going to be easy math now. Okay, for the nitrogens, it's 3 electrons being gained. How do I know which side to add them to? This number is bigger, so I need to add the negatives to that side to bring it down to match. This number is bigger, so I need to add the negatives that side to bring them down to match. Okay, and that's how I got these numbers on either side of the arrows. Okay, cross multiplied to get to this equation. Okay, we're going to have some big coefficients here in a second, but we need to balance out the oxygens and the hydrogens. We have oxygens everywhere. Remember, we balance oxygens by adding water. We balance hydrogens by adding H positives. Okay, this could be a real mess if you did it up in the half reactions. We're just going to do the final equation where it's easier. Okay, we got 21 oxygens going to 28 O's, difference of 7. So over here, we're going to have 7 waters. Okay, balancing those H's, we have 14 H's going to 18 H's. So we need to add 4 more hydrogens to balance that out. Okay, and so that is our final balanced chemical equation. Woo, that's a lot about on redox. Watch it again if you want. Like it. Oxidation reduction is just one of those gigs. You just got to practice it. You need to be fluent with oxidation numbers to really understand it. But seriously, practice it. Go over this final one again. It'll be good times. I'm Dr. Manis. I'll talk to you later. Take care.